Let's start with the definition of a relation, and this is the definition. So a relation is a subset of the Cartesian product of two sets. Okay? So what's the relation? Hold on a second. One person at a time. Raise your hands. Yeah.
Cartesian product.
Wrong. Okay, cool. Yeah, that's the one. Oops. Sorry. Yeah. So, so a relation is a subset of Cartesian product of two sets. If it's a binary relation, if it's three sets, it's tertiary relation, and so on. Okay. The thing is, from this particular definition, you don't get a glimpse into what it should be. Okay, so I'm going to start with a motivating example of where you would see that relationships or relations are quite natural in the way we see things around us. Okay, so ये जो model है, ये जो structure है itself, it's quite natural. Like sets are natural, you know, sets are natural. They're a collection of things. Okay, so they appear natural. You'll see relations are also natural. And here's the example. Example, let's say you are playing I don't know, a game or something, okay? And you have these planes, and what these circles represent, what do you think these circles represent? Yeah.
Type of the plane.
Okay, yeah, type of the plane too, yeah. Yeah. So for this example, what I'm trying to do is, I'm trying to mimic their sensor range. Okay, so for example, for A1, the sensor range is this green circle. Anything in any enemy in this green circle is visible to this guy. Okay, and for example, A2's circle is very small, so he can't see anyone else. Okay, and so on. Yeah. Okay, so they represent the range of the sensors of each of these planes. Okay, so we can write for these planes. We can use set to represent all of them. Okay, since there are 6 of these planes, so we use a set that contains 6 of them. I'm writing them as the set's name is M, and the planes are called A1, A2, A3, A4, A5, A6. Okay, so the Cartesian product of these would be M cross M. Okay, so since there is only one set, the Cartesian product of the set with itself would be M cross M. The relation in here would be who can see who. Okay? So that's the kind of point of the whole exercise, that the relation can model this sense of range thing effectively. Who can see who. Okay? So for example, yeah, A jets, come on in. Has a sensing circle and can see all the jets that lie in its sensing circle. Here's the important point. A can see B does not imply that B can see A. Okay? Alright? So which means that the direction is important. Okay? अगर डायरेक्शन इंपॉर्टेंट ना होती तो हम कुछ और, थैंक यू इरफान, हम कुछ और यूज़ कर रहे होते हैं, हम कार्टेशियन प्रोडक्ट ना यूज़ कर रहे होते हैं. Okay, remember yesterday I told you that elements of Cartesian product are tuples, and the order matters in those things. Okay, the Cartesian product itself is a set. Okay, but the members are tuples. So cool. So let's write down the whole relation here. So this is the complete relation which kind of encodes all of this picture. It says, for example, A1 can see A2. It encodes the information that A1 can see A3, A1 can see A5, A3 can see A5, and A4 can see A5. And none of the other relations are active. None of the other planes can see anything else. Okay, this completely mimics this information that was available to you. Okay, can you guys think of another example of relations in real life? Yeah.
Parent and child.
Yeah, parent and child is a relation too. Yeah, cool, nice. A kind of a nice, simple example is social media. People on social media, if they are connected, you can have a relation between them. If they are not, you discard that relation. Okay. So, for example, if you're on Twitter, there are a couple of users. If one follows the other, you can have a. If one follows the other, you can have a relation. And yeah, so if A1 follows A2, you have a relation A1, A2, and if A2 also follows A1, you will also have A2, A1. Okay. Okay, moving on. Coming back to actually the point is this whole thing is just a subset of the Cartesian product. Okay. So we know that M cross M is a set, right? What's the size of this set in this example? 36. Yeah, there are 36 possible pairs, so you would get 36 as the size of the Cartesian product of the set. I have a question here. Question is follow-up question. Okay, follow-up question is, how many different relations can I construct on this set M? It's 2 raised to the power 36. Awesome. Yeah, that's the number of, for every subset would give you a different relation. Every subset of the Cartesian product in here would give you a different relation, which means you can construct 2 raised to the power 36 different relationships. That's a huge number. Okay? Is it clear to everyone? For every subset of the Cartesian product represents a different relation. Okay, so if you pick, for example, none of the tuples from the Cartesian product, this is a relation which contains none of the pairs. Okay, so for every possible subset of the Cartesian product, you have a relation. So the number of unique, distinct relations you can construct on this set is 2 raised to the power 36. Okay, better now? Okay. Yeah, okay, so if you have a set A, 1, 2, 3, 4, and you have set Z, this is the Cartesian product, and any subset of this thing is a relation. So for example, R is 2A, 3B, 4C, or empty is also a relation, or 2A is just a singleton relation, okay?